All righty, good morning, everyone. So we get to start our last chapter. So this chapter deals with image formation, which is also what we call geometrical optics. We're going to look at two different scenarios. The first one we're going to look at is reflection. So how do we get images from reflection, so i.e. mirrors? And then after that, we'll look at the image formation from refraction, so lenses and things like that wouldn't pass this straight through. So in that case, let's look at it. So first up, we have our reflection. So first one we're going to look at is our plane mirrors. So plane mirror is one where the radius of curvature is simply equal to infinity. So this thing actually is a plane. So here's my plane mirror. So here's my mirror in this case. So beautiful. Here's my mirror. Right. And then we're going to put some object in front of the mirror. So we're going to go ahead and look at this object in our plane mirror. So typically, where we do this is, again, like we kind of talked about in lab, is we're going to draw some principal rays. So my first principal ray I'm going to draw is the ray that kind of comes down in this direction. Okay, so I'm going to call this my principal ray number one. It's then going to strike the mirror at this point. But we know by the law of reflections, this guy has to bounce off at exactly the same angle at which it came in at. So this guy is then going to reflect off in this direction at exactly the same angle. So hopefully I drew that at about the same angle. Okay. So here's this guy. Principal ray number two then is going to be the ray. I'll do that one in red in this case, which I'm going to draw this way. So this guy's going to come down like this. Again, going to strike the mirror at some initial angle here. So again, by the law of reflections, we know this guy has to reflect off at exactly the same incident angle at which it came in at. So let me call this the angle of phi. And this one's going to reflect off at this angle of phi doing something like this. Okay, so this is the same angle as phi. It's okay? Now, in this case, my eye is going to be placed here, which is looking at these reflected rays coming back into my eye. Okay. Now, first thing to notice is, if I drew this thing hopefully properly, these two lines are diverging away from each other, right? So these two guys are slowly moving away from each other, which means that what? They will never actually cross each other, okay? So what my eye does is to see this image here, as we talked about before, our eyes are kind of stupid objects, and the fact that they don't see them cross each other, so they have to ray trace them back to where they think they actually came from. Okay, with this. So this one then is going to get ray traced back in this direction along the line at which it started off at. This one then is going to be ray traced backwards as well. Color haven't used yet. I think I've used pretty much every color. I think so. So I'll do this one. So this one's going to ray trace back this way. And then eventually these two lines are going to cross each other. And where these guys cross each other, this is where we call the image. Okay, so this is our image. So this guy then is going to be our image. So first things first, let's define this distance here as the distance from the mirror to where the image occurs as S prime, which is then my image distance. This distance here, which is the distance from the mirror to where this guy is actually set up, is what we call the object distance. So that's S. This guy's going to have some height to it. Let's call that H, where this is the object height. Cool. And then this guy's going to have some height to it. Let's call that H prime, which is then going to be my image height. This is my image height. Cool. So first thing to notice is that what? This image here is what we call a virtual image. So this creates what's called a virtual image. It's virtual because what? If I took a piece of paper, for example, let's say this is my piece of paper, and I put it at the location of where this image appears to have been created, no light actually passes through the image. Okay, so meaning that if I could reach behind the mirror and I put this piece of paper here, the image would never show up on this piece of paper because the light is going in this direction, which means the light itself starts off on the left side, bounces off, and then goes back to the left side. So no actual light passes through the image itself. This is what we call a virtual image. So again, if I put this guy here, there's no actual image created on there. No light gets collected onto the piece of paper. So this is what we call a virtual image. All right. So from here, if I did some algebraic shenanigans going on here, so what we know is that what? This angle here has to be the same as this angle here. Actually, not that angle, but if I continue this line in this direction, this angle here has to be the same as this angle here by geometrical reasons. And again, if I extend this guy this way, this angle here has to be the same as this angle here. So what I can actually show using geometry, but I'm not actually going to do that, is that S is actually equal to negative S prime. And then H here is going to be equal to H prime. So basically all that means then is this triangle here is exactly the same as this triangle here. And then this triangle here is exactly the same as this triangle here. So basically we have similar triangles. Everything works out to be exactly the same proportions, which means again, that's S prime here is negative of what S is. And then H prime is exactly the same thing as H. So all that means is what? If I was looking at myself in a plane mirror, if I'm standing, say, I don't know, 2 feet in front of the mirror, my image then is going to appear 2 feet behind the mirror. Exactly the same distance, right? The height of my head would exactly be the same height as my head in the mirror. So everything stays exactly the same. Okay, so everything is mirror image, so i.e. it's reverse directions, but that's okay. So this is plane mirrors. So plane mirrors simply say that the image distance is exactly the same as the object distance, just on the other side of the mirror, and the object's height is exactly the same as the image height. About as boring as possible. This is plane mirrors. So this is boring. But anyways, that's plane mirrors. I have a group assignment about this, but I'm going to hold off on that for a little bit. Let's kind of get to the next one, which is more interesting. So now we're going to look at what are called spherical mirrors. So spherical mirrors. So what's a spherical mirror? So a spherical mirror is exactly what it sounds like. So in this case, all you're going to do is you're going to take a sphere. So here's your sphere. And then you're just going to chop off a portion of the sphere. So let's say we're going to chop off this portion. Okay. So in this case, we're going to mirror the sphere. So we're either going to have a mirror on the outside, or we're going to have a mirror on the inside. So it could be that the inside portion is actually mirrored in this case. So all that means then is, let me redraw these guys over here. Is I'm either going to have one mirror where the inside portion is mirrored. So it's going to go this way. Okay, so this guy's going to have some radius of curvature. So this is my radius of curvature, where in this case, my light is going to be incoming inside this way. So it's going to hit the inside mirrored portion of this sphere. Okay, this is what's known as a concave mirror. So this is my concave mirror. So cave, you're going inside of a cave. Okay, the other one then is the back side of this guy. So this guy's going to look this way. We're going to have my radius of curvature. So here's my radius of curvature. And then in this case, my light is going to travel in this direction and hit the backside of the mirror. So this is what we call a convex mirror. Okay? Now, from here, we usually draw this line here, which is the bisecting line, or this guy is what's known as the principal axis. So this is our principal axis. Same thing here. This is the line that bisects this guy. So this is what we call the principal axis. There we go. It's better. So this is our principal axis. So this is the line that actually bisects the mirror. And so in this case, we're going to shine light parallel to the principal axis. Here, we're also shining light parallel to the principal axis. So let's look at what happens in this case. So this one is going to come in happily, strike the mirror, and then what we know is what? Again, by our law of reflections, at this point here, we would have to draw a perpendicular line. So here's my perpendicular line, which means this light ray is going to come in at some angle of theta, and then my reflected ray has to come out at exactly the same angle of theta. So this is going to be my angle of theta here. So this guy then is going to pass through this point. Okay, so this ray is going to bounce off in this direction. Okay. Now, again, if I continue this one here, that one strikes the mirror, has to bounce off again by the law of reflections in exactly the same angle. So this one's going to bounce off in this direction, bounce off here. This one then is going to come in. ray hits here, again, by the law of reflections, this guy has to bounce off at exactly the same angle at which it came in. So this guy's going to reflect off in this direction. And then finally, this one, if I continue this guy, he's going to hit here, and this guy's going to reflect off in this direction. So it's going to bounce through and look something like this. That's okay? So what happens then is in this domain where all these light rays come in, then this area here, all of them are going to be reflected through a particular point here, which is what's called the focal point. So this is what we're going to call the focal points. Where this distance from the back of the mirror to the location of the focal point is what we're going to call the focal length. Hopefully it's doing okay. Now, one thing I should point out here is that the thickness of here, of this guy, so let's call this some thickness of D, has to be less than the radius of curvature. So basically meaning that if I was considering light that came in way out here, what would actually happen in this case is this light, which would be reflected, would actually miss the focal points. Okay, or light that comes in about here, which would hit, also would miss the focal point when it comes to a spherical mirror. So here we're only talking about a collection of light rays that come in at a spread of less than the radius of curvature. Now, in this case, these rays that would come in like this, these create what are known as spherical aberration. So the spherical aberration causes your image to become blurred. So basically what happens then is instead of having a nice crisp focal point, you get a smeared out focal point, which means that something which should look nice and crisp now becomes basically blurred out. So this is kind of a problem when it comes to things like telescopes, where you're trying to look at distant objects. So in that case, if we have the spherical aberration, now we can't really see that distant object anymore because now we get this extra light coming from the outside, which actually blurs then our image. Okay. This would be true if you bought, for example, a cheap telescope, right? Let's say you went to Walmart and spent like $100 on a telescope. You would get spherical aberration in that case. Of course, if you're looking at something like the moon, you don't have to worry about it. But if you're trying to look at something like Saturn and see the rings of Saturn, you might get this blurriness, so you might not actually see it in that case. Now, the way we actually get around that is to use a different type of mirror, or that different type of mirror is actually a parabolic mirror. So a parabolic mirror. So in that case, the shape of it is not a constant radius anymore, but it's actually parabolic in this case. Right? So what happens in that case then is you don't get the spherical aberration anymore. So you actually would then cause the light rays on the outside here to still pass through the focal points if you use the parabolic. So in this case, it gets rid of the spherical aberration. So no spherical aberration. Now, the problem about these is that they are much more expensive to actually create, which means if you spend $100 on a telescope, you're certainly not getting a parabolic mirror. What's up?
Oh, so you said that the spherical aberration happens whenever it's like the very edge light doesn't.
Correct. So basically anything bigger than this kind of central region, then yeah. So any light that's coming in kind of more towards the edges in this case. Exactly. So the light rays in that case will miss the focal point, which gives you this kind of blurring.
So is less than 2R.
Oh, because the way I wrote it. Yeah, I guess we can write it that way. Yeah. I guess the way I wrote it was this way. So yeah. I get that.
I guess the parabolic here isn't that abusing the fact that any like real parabola has a focal point where everything passes through.
Correct. Absolutely. Absolutely. That's why we use those. Exactly. Now, again, you're talking about really huge telescopes in this case. So things that are trying to look at very far distant, objects and things like that. Radio telescopes as well. So, but yeah, just wanted to point that out. So let's talk about this one. So what happens in this case then is this light ray is going to come in. It's going to hit, but it's going to reflect offward. That again, just using our law of reflections. So whatever angle this guy comes in at, he has to reflect off at exactly that angle. So he's going to bounce off in this direction. So my light then is going to bounce off here. This light ray then is going to come in. He's going to bounce off, right? Maybe something very shallow, something like this. This one's going to come in. It's going to hit. It's going to bounce off, say something like this. And this one's going to hit, bounce off, and then be more extreme off in this direction. So this causes the light to hit and spread outward. Right? Now, for both of these cases, my eye is going to be sitting out here. So here's my eye. So in this case, it's looking at the reflected light coming back in this direction. And for this one, my eye is out here looking at the reflected light reflecting backwards. Otherwise, if it was on this side, I wouldn't see anything. So it would be kind of pointless, right? So it has to be on the same side. So in this case, again, our eyes being stupid quantities, they're going to think all of these rays here that are diverging outward all came from a single point somewhere back here. So in this case, it's going to ray trace each one of these lines backwards. So if I ray trace this one, ray trace this one, ray trace this one, and ray trace this one, it appears that all of these light rays originated at this point, which again is the focal point. Okay. So on this one, the focal point is on the front side of the mirror. On this one, the focal point is on the back side of the mirror. And again, this distance here from the mirror to the location of the focal point is called the focal length. So we're going to call that guy F again. So this is my focal length. Now, it turns out that for spherical mirrors like this, the focal length is exactly equal to 1/2 of the radius of curvature. This will always be true for a spherical mirror. So in this case, my focal length will always be 1/2 of my radius of curvature. So if you know the radius of curvature, you know the focal point. Okay. So these are our two different types of spherical mirrors. So let's start talking about image formation from these guys. So how do I get image formation from these two different scenarios here? So first one we're going to concentrate on is my concave mirror. And for our concave mirror, we're going to have 3 different cases. So let's talk about our 3 different cases. Get rid of this guy. So let's look at case number 1. So case number 1 is, here's my spherical mirror. This guy, again, is going to have some radius of curvature. So here's my radius of curvature. We now know the focal length is going to be at 1/2 of that guy. And then case number 1 is going to be, there's my principal axis. So here's my radius, curvature, here's my focal point. So case number 1 is going to be when my object, i.e. my object distance in this case, is greater than the radius of curvature. So in this case, we want S greater than R, somewhere out here. Okay. So let's look at what happens in this case. Now, as I kind of talked about in lab, but we're going to do the same thing here, is typically when we draw these guys, we're going to use typically 2 out of 3 principal rays. So let's talk about the principal rays are. So the first principal ray is the ray that goes parallel to the principal, hits the mirror, and then reflects down through the focal point. So this is principal ray number 1. Principal ray number 2 then is the ray that's going to pass through the focal point. So this ray hit the back of the mirror, and then it's going to reflect parallel to the principal. So this one's going to go in this direction. It's going to come down initially through here, pass through the focal point. I drew that absolutely awfully. Oh, that's better. Hit there and then bounce off. This is principal ray number 2. Now, principal ray number 3 is the one that's going to start at the tip again, but hit exactly the mirror at the location of the principal axis. And then it's going to reflect off. So this one's going to reflect, come in this way. Hit then the back portion of the mirror at the principal axis. Again, law of reflection says whatever angle this guy came in at, this angle has to come out. So this guy's going to come in this direction. And then this is going to be principal ray number. Okay. Now, where all 3 of these guys intersect each other, that is then the location of the image. So this is my image. So the image is where the 3 or at least 2 of these principal rays intersect each other. So my image formation happens where these guys actually cross. Okay? So this is my image. So let's see, what can we say about this image location? And other things we can say about this. So first of all, where is this image located? According to this picture. So this is my radius of curvature. This is my focal point. Where is it? It's in between the 2, right? So this distance then is going to be my distance S prime, which is my image distance. So we can say in this case, S prime is going to be somewhere between the focal length and my radius of curvature. Okay. Now, next thing we can say about this guy is what is the orientation of this guy relative to this guy? Is it in the same direction or the opposite direction? Opposite direction. So this guy's what we're going to call inverted. So we have inverted image, which means that this guy is upside down. And then finally, if I put my piece of paper here, would my image show up on this piece of paper or not? So in this case, my light is coming in this way, reflects off going back in this direction. So it goes from left to right and then right to left. So if I put my paper here, would I see it on the paper? Yes, right? Because the light actually passes through it. So this is what we call a real image. Okay, real. So this is a real image. And the reason for that, again, is that the light passes through it, as opposed to a virtual where the light does not pass through it. Okay? So this is my case number one. So case number one says that if I have my object some greater distance than the radius of curvature, my image will be somewhere between the focal length and the radius of curvature. It will be inverted and it will be real. Okay, let's look at case number two. So case number two is now going to be this one. So here again is my mirror. This is my principal axis. Here's my radius of curvature. And now here's my focal length, or my focal points in this case. And where am I going to put it this time? What do you think? Somewhere between the two, right? So I'm going to put this somewhere between my radius of curvature and my focal points. So in this case, for case number two, my object distance will be between the focal length and my radius of curvature. Okay? So for this one, let's do the same thing. So I'm going to draw principal ray number one, where again, it's going to come in, hit then the mirror, reflect off, and then pass through the focal points. So this is ray number one. Okay. Ray number two, again, is the one that's going to pass through the focal point. Beautiful. Hit the mirror, and then it's going to reflect backwards, parallel to my principal axis. My image then, again, is going to be where these two guys intersect each other, which means it's going to be here for this particular case. Everybody's doing okay? Now, what can we say about this image? So first of all, where is it? Where is it? So where is it? It's outside of the radius of curvature, right? So in this case, we know that what? S prime will be greater than the radius of curvature. Is it upright or inverted? Meaning, is it in the same orientation or upside down? So it's inverted. So this guy's upside down. And is this guy real or virtual? So does the light pass through it? So again, if I put my piece of paper here, does the light actually pass through it? So this guy's real. So for this case, for case number two, if we have our object somewhere between the focal length and the radius of curvature, then the image will be formed outside of the radius of curvature. It will be inverted and real. Now, one thing to note is the closer I get to the focal point, the further this guy is going to be created. Okay, so the closer I am to F, the further away this guy is going to be. So case number three, look at the final case. So this guy, hopefully a little bit bigger. Again, my principal axis. So let's put my focal length here, or my, sorry, radius and curvature here, focal length here. So where is the last place I'm going to put it? Exactly, inside of the focal length, right? So in this case, let's draw this guy somewhere inside of here. Well, there's going to be this guy. So this is my object distance in this case. So case number three. So here, case number three, my object distance will be less than the focal length. So let's draw this one again. So first things first, we're going to draw principal ray number one. So again, principal ray number one is going to be the one that hits here, reflects then through the focal point, and then goes on its merry way. Good. So this is principal ray number 1. Now, in this case, principal ray number 2 is really awkward to draw because I have to try to draw it through this focal point, which is a little bit weird, right? So I'm going to draw principal ray number 3 instead, right? So again, principal ray number 3 is the one that's going to come down, hit the back of the mirror at the location of the principal axis, comes in at some angle of theta. It's then going to reflect off at, again, some angle of theta. Exactly the same angle. Now, again, for all these cases, just like we said before, my eye is here. My eye is here. And my eye is here. Now, in this case, as we can see, my rays out here are diverging away from each other, which means, are they going to cross anywhere here? No. So my eye, being as dumb as it is, right, is going to ray trace each one of these guys backwards. So it's going to ray trace each one to where it thinks it came from, which means where these two ray trace lines cross each other, I don't have quite enough room, so I'm going to kind of approximate, is going to be the location of my image. So my image is going to be somewhere about here. So this distance now is going to be my image distance. And let's talk about this guy. So first thing we notice about this is what's true about the image distance. Coming the other direction, so this guy we're going to say is actually negative. So we're going to have a negative image distance, right? So my image distance in this case will be less than 0 because it's on the back side of the mirror. Is this guy upright or inverted? So is it in the same orientation or opposite? What's up? It's going to be upright. Fantastic. So this is upright. And then finally, is this guy real or virtual? It's virtual, right? So this is going to be a virtual image. Fantastic. So this is how we draw these things. These are what are known as ray diagrams. Or ray diagram. Absolutely expect to draw one of these on exam number 5. Okay. What's up, kid?
And so the light reaches the eye because of the weight, right? Like it's spreading out there.
Correct. Yes, correct. So again, all we're doing here is we're drawing the rays, but again, each one of these rays represents a plane wave moving in that direction. Excuse me. Absolutely. Yes, absolutely. Is okay? So again, case number 1 is when we are outside of the radius of curvature. The location of the image will be in between the radius of curvature and the focal length. It will be inverted and real. Anytime we are inside of the radius of curvature, but outside of the focal length, our image will be created outside of the radius of curvature. It will be inverted and real. And anytime we are inside of the focal length, it will always be negative for the image position, upright and virtual. Okay. So last one we have to do then is our concave mirror. So let's do our concave. Now concave, we only have one case, so I'm not going to belate this too much. So we're just going to draw our one mirror. So this is my concave mirror. So this is my principal axis. This is my radius of curvature. And again, here's my focal point halfway across there. So let's draw this one. What the? Oh, did I write concave? Yes. Sorry, convex. Good thing somebody's paying attention. Okay. It's okay. So let's do this one. So my image, or sorry, my object is going to be out here, right? So this is going to be my object distance, S, where S in this case will be positive. And let's draw this guy. So, okay, so in this case, again, we're going to draw principal ray number 1. So principal ray number 1 is going to be the one that goes, again, parallel to the principal. It's going to hit the mirror, but it's going to reflect off as if it came from the focal point. So I'm going to trace this guy down to my focal point. Fantastic. And then this guy's going to reflect off along that direction there, as if it came from the focal point. So this is my principal ray number 1. Principal ray number 2, as we said before, is going to be the one that tries to go through the focal points here. So this guy is going to try to go through the focal point, but by the time it hits the mirror, it has to reflect back parallel to the principal. So this is principal ray number 2. Okay. Now again, just to clarify, my eye is out here watching the entire thing. Now again, what my eye sees are these two lines are diverging away from each other, right? They're spreading out. So again, my eye being a stupid thing is going to ray trace each one of these guys backwards. So it's going to ray trace this one back to where it thinks it came from. So back to the focal point. Broke my chalk, as always. And then it's going to ray trace this one backwards to where it thinks it came from. And where these two ray trace lines cross will be the location of my image. So this is going to be my image. So this is going to be my image distance S prime. So just like this one here, S prime will always be negative. So this is going to be negative. Is that an, excuse me, upright or inverted? Upright. So this is going to be an upright. And real or virtual. So does any light actually pass through it? No. So this is virtual. So this guy is virtual. So this will always be true for a convex mirror. So the image will always be behind the mirror. It will always be in the same orientation, i.e. upright, and it's always going to be virtual. So one other thing to note here is that as S prime gets closer and closer to the actual mirror itself, this guy is going to move in this direction, get closer and closer and closer to the mirror, and grow in size. Okay, so the further this guy gets away, the closer it gets to the focal point, and the smaller it's going to get. The closer the object gets to the actual mirror itself, the closer the image is going to get to the mirror, and the bigger it's going to get. Okay. So cool. So these are what we call the ray diagrams. So this is how we actually determine the image location. Now from here, we have two choices. We could determine the size of the image and where it is if we brought in things like rulers and we measured all these things. I know sometimes as you guys with engineers, you love your rulers and measure things. So, drawing straight lines and all that cool stuff. So that's one way to do it. But is that very precise? No. So what we want to do then is come up with an equation that talks about all these things, which is where the geometric part comes from. Is basically we would then use geometry to show this stuff. And I'm going to skip that part because I know actually nobody cares. And we're going to come up with what's known as the lens equation. So what the lens equation says is how we actually determine the location of the image is by taking 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Does this look familiar? Lab, right? But that was mirrors, which is nice about this is because actually the lens equation is the same as the mirror equation, which means everything we're going to do for this entire chapter depends only on 2 equations. Good. And we also have known as the magnification, just like we did in lab. So magnification is the size of the image. So this is my image height H prime. This is my object height H. So this says my magnification is then the ratio of the image height to the object height, which is equal to negative of the image distance divided by the object distance. So this is what's known as the magnification, so the size of him. Now, along with this, we're going to have a couple sign rules here. So let's talk about our sign conventions. Sign conventions. And there we go. So sign convention number 1 has to do with the focal length itself. So if I'm dealing with a concave mirror, the focal length will always be positive. So this is for concave. If I'm dealing with a convex mirror, my focal length then will be negative. So this is convex. Okay. So this is rule number 1. Rule number 2 is that my object distance will be positive if on same side light is coming from. Now, 99% of the time, this will always be positive. Okay? Unless I have a combination of stuff, which is why it's not always going to be positive. But for the most part, as long as it's on the side that the light is coming from, i.e. over here, it's a positive object distance. If it's on the opposite side, it's negative. Okay. Rule number 3 is my image distance will be positive if on the same side, the light is going to. flashy. So meaning in this case, this image distance here, which is what? This distance is positive because it's on the same side the light is going to. So again, my light starts off on the left-hand side, goes to the right, but then reflects from the right to the left. So since my light is going in this direction, it's on the same side that the light is going to, which makes it positive. Over here, my light is going from the left to the right, hits the mirror, goes from the right to the left, which means that this guy is on the opposite side that the light is going to, because my light is going to the left, which makes this guy negative. It's okay. Finally, the last one, write that over here. Number 4 is the magnification is positive if it's upright and negative if inverted. Okay. So if it's inverted, my magnification will be negative, like we saw in lab, or it's going to be positive if it's actually upright. It was okay? Not too bad. Pretty easy stuff, right? So let's use this. Let's start doing some examples of this, and let's see how this actually works. So let's look at this example over here. So let's ask that we have a 1.5 centimeter tall diamond ring is placed 20 centimeters from a concave mirror. So that's the one that you're going inside of, with a radius of curvature of 30 centimeters, which means the focal length is then 15 centimeters. It wants me then to determine the position of the image and then finally its size. So let's talk about this. So let's draw this. So first of all, just to get practice drawing ray diagrams, let's draw the ray diagram. So here is my object here. So this is my mirror. So this is my radius of curvature. Here is my focal length. So again, this is 30, which means this guy's 15. Okay. It says then that my object is placed 20 centimeters, which means it's just outside of the focal length, which means this guy is going to be somewhere about here. Okay. This has a height of h, which is 1.5 centimeters. We know again that this distance is 15 centimeters, which is our focal length. And then we also know our object distance in this case is s, which is 20 centimeters. Okay. So let's get some practice. So my ray number 1, again, is going to be the one that goes parallel to the principal, hits the back of the mirror, so putting that at this location, goes through the focal point. So it's going to go off in this direction. So that's ray number 1. Ray number 2, again, is the one that goes through the focal point on this side. It's the back of the mirror and then gets reflected back in this direction. So this is now ray number 2. And again, where these guys intersect each other, this is going to be the location of my image. What's that?
Started doing it.
So because again, what I'm considering are only small rays that are coming in like this region. So even though I'm kind of drawing it this way, since the rays are coming in and hitting here, I'm trying to match it up with the actual back of the mirror because I'm, again, only considering a small area of rays because otherwise I get that spherical aberration. So that's the only reason I'm kind of taking that out a little bit further. So exactly. Now, do you have to do that when you're drawing it? No, not really. But again, just trying to make it a little more apparent. But it's so cool. So in this case, again, this is going to be my image distance of S prime. So our expectations in this case, let's talk about our expectations. So we should get that S prime is what? Greater than the radius of curvature. Because again, as we talked about, case number 2, when it's on the inside, this guy should be inverted, which means my magnification needs to be negative. Right? We also can see that it should be bigger than the actual object itself, which means the magnitude of my magnification should be bigger than 1. And this guy should actually be real. So these should be our expectations. So good. So let's now use the lens equation. The lens equation says 1 over the image or object distance plus 1 over my image distance is equal to 1. Now, in this case, my object distance is positive because it's on the same side that the light is coming from. My focal length is positive because this guy is a converging mirror, or also known as a concave mirror. Okay. So in this case, we want to know simply this guy. So let's do that. So I get 1 over S prime is equal to 1 over S minus 1 over S. Let's find a common denominator because I like algebra. So it's going to be an f times s, right, on the denominator. And then my numerator is going to become s minus f, right? Invert that, so s prime then is going to be equal to the focal length times the object distance divided by the object distance minus the focal length. Now, again, do you have to do that? Of course not. I just like algebra. You guys know that about me by now. And we're like, okay, so now from here, let's plug in some numbers. So let's do that. So in this case, my focal length is 15 times my object distance, which is 20, divided then by my object distance, which is 20 minus 15. And this is all going to have units of centimeters, right? So this is going to be the same thing then as what, 5, right? That's going to cancel out with that, which makes that 3. And what's 3 times 20? 60. So this guy's going to be the same thing as 60 centimeters. Okay? Assuming I did my math right. Okay. So again, going back to my expectation, S prime should be bigger than the radius of curvature, which it is. It's actually double the size of the radius of curvature. Okay, cool. So now, from here, we want to know what is the object, or sorry, the image height. So let's start off with the magnification. So we know the magnification is equal to the image height divided by the object height, which is also equal to negative of the image distance divided by the object distance. Okay. So from here, this says then we can find the image height, which is then equal to negative of the image distance divided by the object distance times the object height. Okay? So from here, this then becomes minus positive. So this is going to be 60 centimeters divided by 20 centimeters, all times the height. So from here, my magnification is actually just this term. So I'm going to write that over here. So my magnification is actually minus 60 divided by 20, which is the same thing as what? Negative 3. Which means that what? As we said here, it has to be inverted, which means it's negative. And because this guy is bigger than him, my absolute value or the magnitude of this guy has to be bigger than 1, which it is. Okay? Based off of our picture. Cool. So let's plug that in here. So this is going to be the same thing as what? Negative 4.5 centimeters, because this guy was what? 1.5 centimeters. And assuming I can still do basic math, which I sometimes have problems with that. What happens when you know too much higher level math? Basic math kind of goes to 0. Anyways, so this thing should be negative 4.5 centimeters in height. And again, negative sign just means it's inverted. It was okay? Let's do another one. So this says we have an external rear view mirror. So for those of you in Evansville and don't know what a side view mirror is, it's the mirror that's on the side of the car. Okay. So this says it's a convex mirror with a radius of curvature, which is 16 meters. And also to determine the location in the image and its and its magnification for an object, which is 10 meters and from the car. So in this case, behind the car. So when you actually go to merge lanes, you can look in that and find out there's somebody actually there. That's what these things are for. Okay. I know you're not taught these things in Evansville. Okay. Everyone's okay? Fantastic. So let's draw this picture. And again, let's draw our ray diagram. And then we'll apply the math from there. So good. So this thing says that we have our convex. And again, our convex looks like this. So this is my convex. Good. So this is my principal axis. There's my principal axis. And it says this guy has a radius of curvature, which is 16 meters. So meters. So here's my radius of curvature. Here then is my focal point, which means my focal length then again is 1/2 of the radius of curvature, which means that this guy then is going to be at least absolute value. I'm going to write it this way, which is then 8 meters. So this is my absolute value of this guy. Of course, it's actually negative, but I'm going to use that later. So in this case, if this guy is 8 meters, we now have the object, which is a little bit further than that. So it's about 10 meters. So this guy's going to be sitting about here. Okay, so this is my object. Again, let's draw our principal ray. So principal ray number 1 is going to be the one that hits the mirror, reflects off as if it came from the focal point. So this guy's going to go in this direction. Ray number 2 is going to be the one that tries to go through the focal point over here, but it can't because it has to reflect back parallel to the principal. Where the image is formed again is where we ray trace this guy backwards in this direction. This one gets ray traced in this direction. So my image formation will be created here. So in this case, we should find that S prime is negative, and that's what? My magnification is less than 1, but it's positive. Okay? So it's less than 1 because it's shrunk down, so it has to be a fraction, and it's positive because it's upright. So cool, so let's do the same thing. So now we have 1 over the object distance plus 1 over the image distance is then equal to negative 1 over the focal length. Again, it's negative because this is convex, so we know the convex has to have a negative focal length. So from here, we get 1 over the image distance is equal to minus 1 over the focal length plus 1 over the object distance, because when I move it over, it becomes negative. Again, finding common denominator, this guy then becomes negative the focal length times the object distance divided by the object distance plus the focal length. Everybody's doing okay? So this then is my image distance. So cool. From here, so we're going to plug in some numbers. So we get a negative focal length is 8 meters. Object distance is 10 meters, divided then by 18 meters. So we're going to get an 80 divided by 18, which is not a whole number. So according to that, that works out as negative 4.4 meters. And again, we said this guy should be negative, which it is. Okay. Last thing then is they want us to find the magnification. So let's do that. So my magnification M then is going to be negative of my image distance divided by my object distance. So it's going to be negative 4.4 divided then by 10, which is the same thing as positive 0.44. So again, we said this guy has to be positive because it's upright, which it is, and it has to be less than 1, which it is because it's 0.44. No, because it's a distance divided by distance. So yeah, so no, that's dimensionless. So no units on that guy. Good question. Good question. So just saying it's, in this case, decreased by, what would that be, like 44%, right? Is basically all that means. Or it's 44% of the original size. Say it that way. It's probably a little bit better. That was okay. That's pretty much it. I mean, that's it for the mirrors, right? So Monday then, we'll start off with a couple group assignments. One dealing with plane mirrors, some dealing then with spherical mirrors, and then we'll do the last part, or almost the last part, which has to do with lenses. So we'll look at image formation from lenses, and then we'll look at combinations of these things. How do we actually combine them together, which is what we did in the lab. And then finally, we'll talk about what happens when we have different radii. So that's what's known as the lens-Baker equation. And then we'll be done. And that's it. Then you'll never have to see me. No, unless you want to. All right, have a good weekend, everybody. Life will be fantastic.
So,
What's that?
like, what if you have like, so you know